Today, we are going to pull back the curtain on something that looks, well, incredibly intimidating: complex circuit diagrams. But I want you to think of them less as a scary problem and more like a puzzle we're about to solve together. So let's just dive right in.
Yeah, we've all been there, right? You look at this spiderweb of components and your brain just kind of goes blank. It seems impossible. But what if I told you there's a secret? A way to make all of that messy complexity just melt away.
Just look at this. On the left, you've got a voltage source and two resistors. And on the right, the same source, but with just one resistor. Now here's the trick. As far as that power source is concerned, these two circuits are identical. They behave in exactly the same way. That, right there, is the magic of simplification.
And this brings us to the hero of our story today, the equivalent component. It's basically a stand-in, a single, simple part that we can swap in for a whole messy group of other parts. And once we do that, the math and the analysis become so much easier.
Okay, so let's start with the most common component out there, the resistor. Because once you get the hang of combining these, you'll have the foundation for literally everything else we're going to talk about.
First up, resistors in series. Just notice how they're connected one after another, end to end. What this means is that the electric current has only one single path it can take. It has to flow through the first one and then right on through the second one. No other choice.
And you're going to love this part. The math could not be simpler. To find the total or equivalent resistance, you just add their values together. That's it. It's beautifully straightforward.
All right, now for the other setup, parallel. See the difference? The current flows along, hits a fork in the road, and splits. Some of it goes through the top resistor, and the rest goes through the bottom one. It's like a river splitting into two smaller streams, only to join back up again later on.
Now, for parallel resistors, the formula looks a little different. We have to work with reciprocals, or 1 over the value. So the reciprocal of the total resistance is the sum of the reciprocals of all the individual resistors. Now hang on to that idea of using reciprocals. It is definitely going to pop up again.
Okay, let's move on to our next component, the inductor. And I've got some really good news for you. You've actually already done all the hard work. You already know the rules.
So here we go. Inductors connected end-to-end, in series. Does that look kind of familiar? It really should. It's the exact same setup we just saw with resistors. The current only has one road to take.
And the formula for the equivalent inductance? Well, you probably guessed it. It's identical to series resistors. You just add them up. See? No new rules to memorize. Easy.
So, what do you think happens with inductors in parallel? Well, take a look. Same structure. The current comes in, it splits up, goes through each inductor on its own path, and then joins back together. It's the same parallel idea all over again.
And yep, this just confirms the pattern. The formula for parallel inductors is that same reciprocal addition we used for parallel resistors. So just like that, you've already mastered the rules for 2 of our 3 big components. See? You got this.
All right, you've seen the pattern for resistors. You've seen that inductors play by the exact same rules. You're probably feeling pretty good right about now. But get ready, because our final component, the capacitor, is about to throw a wrench in everything.
So here it is. Here's the big twist. Capacitors do the complete and total opposite of what we just learned. They take the rules for resistors and inductors and they just flip them completely upside down. This is the one big, giant exception you have to remember.
So have a look at these capacitors in series. Now, based on the pattern we've established, your brain is probably telling you, oh, just add them up, right?
Well, nope. For capacitors in series, we use that reciprocal formula. That's the rule that resistors and inductors use for their parallel connections. It's a complete flip-flop.
Okay, so if series capacitors use the parallel rule, what do you think is going to happen when we actually put them in parallel, like you see here?
You got it. They follow the simple addition rule. To find the equivalent capacitance for capacitors in parallel, you just add their values together, which is what resistors and inductors do in series. The rules are totally swapped.
So we've gone through resistors, we've covered inductors, and we survived the big capacitor twist. Let's pull this all together into one simple, powerful toolkit that you can use for pretty much any circuit. Think of this slide as your master key. It's got all the rules in one spot. You can see it clear as day.
Resistors and inductors are partners in crime. They follow the exact same logic. And then you've got capacitors, the rebels, doing the exact opposite. This is your ultimate cheat sheet for simplifying circuits. We've spent all this time learning the how, but let's take a second to talk about the why. I mean, why is it so important to know how to do this? Why does any of this really matter?
Well, it matters because this is the bedrock of all circuit analysis. This is the first step that turns a problem that looks impossibly complicated into something you can solve with just some basic algebra. It doesn't matter if you're designing something brand new or just trying to fix something that's broken, this skill is absolutely essential.
You know, when we started, we were looking at a complex, tangled web, but now you have the tool to untangle it. You've got the key. So the only question I have left for you is, what complex circuit are you going to unlock next?